Integrated circuit manufacturing is a big business in today's world. Integrated circuits are critical in so many areas of life and are moving into more and more areas all the time. Manufacturing of integrated circuits is a complex, expensive proposition, and in today's world there is as much cooperation as there is competition in the integrated circuit manufacturing business. Integrated circuit manufacturing is another step forward. In the Industrial Revolution, production increased when standardized interchangeable parts were created and when the assembly line was brought into place and there was greater efficiency in assembling items. In the manufacture of integrated circuits, we see that this is extended so that electronics mass produces and builds in the assembly process. It uses standardized parts with the simultaneous manufacture of the wires, the components, the connections, the insulators. This adds increased performance, and increased performance is also added as you expand the circuit elements and have additional larger circuits. Further, integrated circuits greatly reduce the energy needed for control and automation of certain processes. It all starts with the magical silicon crystal. Silicon crystal is an amazing material. It tends to form its own crystal structure, likes to form it, and prefers it. But when it's combined with oxygen, it forms a layer of glass, which makes an excellent insulator and also is a good material for patterning other layers of the silicon wafer. When you add dopants into the crystal, that is, elements from either column 3 or column 5 of the periodic table, you can develop two different types of wires that are embedded in the silicon crystal, and only minute amounts of these dopants need to be added. With proper design and placement of the dopants, there is a possibility of providing a lot of control of the direction and voltage of the direction of currents and voltages using very small input signals. The silicon wafer goes through several manufacturing steps. There is oxidation to form a layer of insulation. Photoresist and etch allows us to transfer a pattern to the wafer, and deposition of materials prepares for both P-type and N-type wafer locations, and drive-in adjusts it where it should be in the wafer. On top of that, we now add in the same types of processes wire connections. Again, we form glass isolation that can then be used to deposit and patterning of the wire metal. And finally, the entire chip is wrapped in a glass isolation for protection with patterning of locations for metal connections to the actual chip to be made. The wafer manufacturing steps include oxidation, which creates a layer of insulation and also creates a layer that can be used for patterning. Photoresist is deposited and then etched. This allows us to transfer a pattern from a separate wafer, from a separate mask, glass sheet, onto the wafer. Deposition, where we introduce a small amount of dopant elements and drive in to create the vertical depth and give the crystalline silicon repair. The wafer manufacturing steps include taking an incoming wafer and depositing either silicon dioxide or another material. Then photolithography adds a layer of photoresist, which is exposed and developed to create a pattern. That pattern is used to etch the layers below. The photoresist is stripped off, the wafer is cleaned, and we now deposit a new material, a conducting material, in order to make our wafer into a circuit. Integrated circuit oxidation is a process in which the wafer is baked at a high heat and either oxygen or water vapor is introduced. The wafer rusts, much like a metal pipe in your backyard would rust, forming a layer of silicon dioxide. Silicon dioxide is a glass. It blocks deposition of materials into unwanted areas. It insulates wires from each other, and it forms gates which allow control of large currents with small voltages. Dry oxygen introduced into the wafer creates thin, dense layers, and steam creates thicker glass layers that grow much more quickly than does the dry oxygen. Photoresist and etch. Photoresist is used to form patterns on the wafer. A photoresist paint is spun onto the wafer. It's baked to dry the resist. Then it is exposed to a patterned light, and the developed material then dissolves areas that are unwanted to form the pattern on the wafer. The photoresist patterns are used to mask the glass beneath it so that the acids will remove areas of the glass that are unwanted and leave glass layers in other areas. The photoresist is then stripped off. The glass pattern is then used to deposit or pattern a deposit in the exposed areas only. Other areas are not deposited. The photoresist, the N-type wafer, has a layer of silicon dioxide. The photoresist is applied. The mask is used. The light exposes the area. And after the mask is removed, the resist is developed. It is used to mask the oxygen layer, and then the oxygen layer is used to provide a mask for the substrate material itself. Photoresist and etch are often done, removal is often done in a wet bath. Deposition then could include a slurry on the surface of the wafer or ion implantation. In an ion implanter, an ion source of a particular metal is introduced. It is separated in a magnet so that only the right metal ion is then shot by way of a large electric and magnetic field into the wafer itself. After the deposition, the source is removed for the next process, which is drive-in. Chemical ions on the surface or very close to the surface are baked deeper into the wafer. Time and temperature are carefully controlled to create the correct vertical depth and to repair the crystal. Wire interconnects are formed in much the same way. First, a layer of glass is deposited. Photoresist patterning is used to create wire holes to layers below. A metal layer is deposited, and photoresist patterning of the metal layer that has been deposited creates connections from one wire to another. The final process step is an oxidation layer that protects the entire chip and is only removed in pattern for the connections from the chip to other elements within a circuit. Manufacturing is complicated and expensive. Therefore, much of the workload is divided into specialists who concentrate on laying photoresist, developing it, or using an ion implanter, or laying down metal layers. The manufacture of integrated circuits is continually improved and pushed. The device sizes, the materials that are used are reduced, and a very correct design prior to the manufacturing process is required. It's important to have effective circuit modeling and layout and use of good quality tools to monitor both the manufacturing process and the models and the circuits that you're trying to produce. Manufacturing is complicated and expensive, and international partnerships have developed. The International Technology Roadmap for Semiconductors has been in existence for many years, and it is an international partnership with countries from all over the world. They try to predict the issues in manufacturing over the next 15 years, and they cooperate as much as they compete with each other to develop new tools, new chemicals, and new processes so that integrated circuits can be manufactured to meet the continuing demands of modern life. Integrated circuit chips require deposition of a layer, deposition of photoresist, transfer of the pattern and etch, deposition of dopants, drive-in, and anneal. It is an expensive, complicated manufacturing process that enables us to have many of the newest devices, newest connections, newest materials, life monitoring items that we have in today's world. But it does require effective, detailed modeling and automatic control of many of the manufacturing processes.